Welcome to Math TV with Professor V. In this video, we're going to look at finding limits of functions with absolute value. So if you haven't already watched how to rewrite absolute value functions piecewise, I'm going to link it up here. Make sure you're comfortable and very capable doing that because that's going to be the first step before we find any of the limits in the examples I'm going to consider now. All right, so find the following limit, and don't worry, there's absolute value right here in the denominator. So we need to find the limit as x approaches 0.5 from the left of 2x minus 1 over 2x cubed minus x squared. So as I mentioned, the first step is always going to be rewriting the absolute value portion as a piecewise function. So in order to do that, I need to identify what the zeros are for the expression inside the absolute value, namely 2x cubed minus x squared. So to find the zeros, I'm just going to set this equal to 0 and then factor. I can factor pretty easily, right? We can just take out an x squared and then I'm left with 2x minus 1. So right away I notice, all right, x squared, that's always going to be positive, worst case 0. And then 2x minus 1 is really controlling the sign of the expression inside the absolute value bars. So basically, I'm going to break up my domain for the absolute value expression at x equals 1/2. So we can rewrite the absolute value of 2x cubed minus x squared as follows. For x values that are greater than or equal to 1/2, everything inside the absolute value bars will already be positive. So taking the absolute value does nothing. So I just have 2x cubed minus x squared. And then for x values that are less than 1/2, then the expression inside the absolute value is negative. So taking the absolute value makes it positive. So I have a negative 2x cubed minus x squared. Okay? And you can just confirm pretty easily, like pick a number greater than 1/2. Say 1, okay? If you plug in 1 for x, notice 2 times 1 cubed minus 1 squared. That's a positive number. So we broke everything up properly. Pick something less than 1/2 to confirm. Say 0. Well, it's 0. That's not a good example. Say you pick -2, then the quantity inside is negative. Okay? Good. Now we're ready to roll and take the limit. And we're going to be careful which portion of the piecewise function we're working with, since we are approaching 0.5 from the left. So the numerator, that's just 2x minus 1. Now for the denominator, since we're approaching 0.5 from the left, we're approaching 1/2 from values that are smaller or less than 1/2. So that means I'm working with this portion of the piecewise function. So now I'm going to go ahead and replace the denominator with negative 2x cubed minus x squared. All right, very good. And notice I'm not able to plug in 1/2 right now because I would get a 0 in the numerator and a 0 in the denominator. But let's go ahead and see if we can factor and then evaluate the limit. So this is the limit. X approaches 0.5 from the left. 2x minus 1 over, and we've already factored that expression that's in the denominator before. I can take out an x squared, and then I have 2x minus 1 left over. Very nice. Okay, so notice now I can cancel out the 2x minus 1, and then we have simply the limit as x approaches 0.5 from the left. In the numerator, there's just a 1. And to make things look nicer, I'm going to put that negative in the numerator with the 1. Don't leave your negatives in the denominator. Either put them in the numerator or just put them outside the expression, okay? And then all that we have left in the denominator now is an x squared. Okay, fabulous. Now I can go ahead, just use direct substitution, meaning plug in wherever x is going to find the limit. So x is going to 0.5. Doesn't matter that it's from the left anymore. That just helped me pick the correct part of the piecewise function. So we have 0.5 squared. Okay, please do not grab your calculator. You can do this, all right? 0.5 squared is 0.25, correct? All right, so this is -1 over 0.25. 0.25 is 1/4, right? 4 quarters make $1. So 1 over 1/4, that's 4. And then don't forget the negative, -4. Yes, good job. It's definitely appropriate to use a calculator sometimes, but other times it's inappropriate. We can do these things in our mind. All right, let's look at some more examples. Next one I have for you is the limit as x approaches 0 from the left of 1 over x minus 1 over the absolute value of x. All right, we can just use straight up definition of absolute value of x for this problem. So remember, absolute value of x is equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. So I have to pay close attention now. We're approaching 0 from the left, so from values smaller than 0. So that means I'm going to use this portion of my piecewise function when I replace absolute value of x. So I'm going to replace it with -x now. So we have here the limit. X approaches 0 from the left, 1 over x minus 1 over -x. All right, good. Not too bad. Now we have here the limit as x approaches 0 from the left. This is 1 over x plus 1 over x. Ooh, and they have a common denominator, so I can add those two terms together. We have the limit x approaches 0 from the left of 2 over x. All right, now this limit is tricky for a lot of students. So when you have the numerator approaching a constant that is not 0 and the denominator is approaching 0, that means the entire expression is approaching infinity. You have to figure out if it's going to be positive infinity, negative infinity, or if you can't decide, then the limit does not exist. So the numerator is just 2. It's just straight up 2. It's not changing. That's positive. And then the denominator is approaching 0 from the left side. So that means coming from values that are smaller than 0. So coming from values that are negative. So the sign of the denominator in this expression is negative. Okay? That means this entire expression here, positive over negative, is negative. While x is approaching 0, think if the denominator is shrinking, that means it's approaching like -0.1, -0.01, -0.0001, etc. It's getting really, really tiny. And when you divide by something getting smaller and smaller and smaller, this whole expression blows up. It gets really, really big. Play around with it in your calculator just to see. So 2 over x is getting really, really large, but in the negative direction. So this limit is -infinity. All right. Now, sometimes if you check the back of the book, it might say something like does not exist because it means the limit's not a finite number. But I like my students to be more specific. And if you can identify that at least the limit is positive infinity or negative infinity, for them to state that. All right? Good. Let's look at another example. Here we have the limit as x approaches -5 from the left of x plus 3 times the absolute value of x plus 5 over x plus 5. So off to the side, let's just consider how we would rewrite the absolute value portion as a piecewise function. So absolute value of x plus 5 just by looking, I'm going to split the domain at -5, right? So x plus 5 is already positive if x is greater than or equal to -5, and then I need to take its opposite for all x's that are less than -5. Good. All right, so now let's see. For part A, we're looking at the limit as x approaches -5 from the left. So from the left, that means I'm working with this portion of my piecewise function because we're coming from the left side or values that are smaller than -5. So now I'm going to write this as the limit. X approaches -5 from the left of x plus 3 times, now be careful. So instead of writing absolute value of x plus 5, I'm going to put the opposite of x plus 5 over x plus 5. See that? Ooh, that's not what I wanted. Okay, I'll draw it myself. Good. Then from here, we can simplify a bit, so we can take that limit. So notice I can cancel out x plus 5. And then now I have the limit. X approaches -5 from the left. Let's put this negative that's right here just outside so we don't lose track of it. Okay, it looks so strange smushed in there. Negative x plus 3 in parentheses. Okay, and then now we're all set. We can just use direct substitution and simply plug in -5 for x. Love it. So we have -5 plus 3. -5 plus 3, that's -2, and then take the opposite of that. This is 2. Okay, very nice. Part B now asks for the limit as x approaches -5, but do you see what's different this time? From the right side. So all that means for us is when we replace the absolute value of x plus 5, we're going to use the other part of our piecewise function because we're approaching 5 from the right, so values that are, -5 from the right, so we're approaching from values that are larger than -5. So I'm just going to replace absolute value of x plus 5 with x plus 5. Okay, so we've got the limit. X approaches -5 from the right. We have x plus 3 times x plus 5 over x plus 5. That just all cancels out to 1. And then now we can go ahead, just directly substitute in -5 for x. So we have the limit, x approaches -5 from the right of -5 plus 3. And that is -2. All right, good. How are we doing? Okay so far? Good, good, good. And then last part of the problem, notice it asks for the limit as x approaches -5. It doesn't tell you from which side. That means it's a two-sided limit of the same function. So notice here we already found in parts A and B the limit from the left and the limit from the right. And first thing that catches my eye is that they are not the same. And we know then that that means that the limit as x approaches -5 for the same function does not exist. And you can say because the limit as x approaches -5 from the left of this function, they didn't call it anything, so I'm just rewriting it, okay, does not equal the limit as x approaches -5 from the right of the same function. Okay, that's your justification. So that limit does not exist. Lovely. I got one last example for you guys, and I really think you can probably do this one on your own. So I say, why don't you pause the video, give it a shot, and then I'll still solve it, but you can check your work along with me just to make sure that something's sunk in. So we have g of x equals x squared plus x minus 6 over the absolute value of x minus 2. find the limit as x approaches 2 from the right of g of x. Part B, find the limit as x approaches 2 from the left of g of x. And then part C, find the limit as x approaches 2 of g of x. So pause it, give it a try, and then check back in. Okay, did you do it yourself? I certainly hope you did. That's the true test. Okay, let's just rewrite the denominator. So just the absolute value of x minus 2 piecewise. Now we're old pros at this, so we know we're going to split the domain at 2. So absolute value of x minus 2 just equals x minus 2 if x is greater than or equal to 2, and negative x minus 2 if x is less than 2. All right, so for part A, we need the limit as x approaches 2 from the right of g of x. So here's g of x squared plus x minus 6 over absolute value x minus 2. Well, since I'm approaching 2 from the right, I'm going to use the top portion of my piecewise function, right? Because that's where we're approaching from values that are greater than 2 from the right side of 2. So that means I'm just going to replace the denominator now with x minus 2. No more absolute value necessary. And then while we're at it, let's just factor that numerator. X squared plus x minus 6, that's going to factor into x plus 3 times x minus 2. And then bam, bam, x minus 2 cancels. We love it. And we have the limit as x approaches 2 from the right of x plus 3. All right, and now we are good to go. Just substitute in 2 for x. So this limit's going to be 2 plus 3, which is 5. Voila. All right, good. Part B, now we're finding the limit as x approaches 2 from the left. All right, so B, limit x approaches 2 from the left of x squared plus x minus 6 over absolute value x minus 2. Okay. You know what? I kind of want to move this over so we can still see both at the same time. Hold on. Bear with. So now let's think about which part of the piecewise function we're going to use. See, I should have done that. Okay, so since we're approaching from the left of 2, then I'm going to use the bottom portion of the piecewise function because that's how the absolute value of x minus 2 is defined for values that are smaller than 2. All right, great. So we have here the limit x approaches 2 from the left. I'm going to replace the denominator now with opposite of x minus 2. Just leave that negative outside the parentheses, okay? Don't distribute it. And then we have the numerator factoring in the same way, x plus 3 times x minus 2. Good. And then we can cancel out that x minus 2 just like last time. And see that negative hanging out down there? Don't forget about it. So I'm going to move it outside the parentheses that are in the numerator. So we've got the limit, x approaches 2 from the left, negative x plus 3. And then now to evaluate the limit, I can just use direct substitution, just plug in 2. So we've got negative 2 plus 3, which is negative 5. Great. Now, last part asked for, see, part C, the limit as x approaches 2 of g of x. So the limit as x approaches 2, and now they're not saying from which side we're approaching. So if they're not saying from which side, then they better be the same. That way they don't have to specify. That's how I think about it. So you check. Were the limits from the right-hand side and the left-hand side equal? No way. One was 5, one was negative 5. So what do we say about this limit? It does not exist. All right. And give them a little justification. Let them know You weren't guessing. You know what's going on. So the limit as x approaches 2 from the right of g of x does not equal the limit as x approaches 2 from the left of g of x. Beautiful. Beautiful, beautiful. All right. So that concludes the video. Hope you found it helpful. If there's any other sort of topics that you would like to have some examples or videos of, please let me know. I'm more than happy to take requests, and happy studying.